in there that represents the targets, the potential targets for MSL to go and try to evaluate the habitability of Mars. And the red dots that you see represent the 60 locations that were proposed by science team members, by the science community, and evaluated during these workshops. The 4 blue dots that you see there, Eberswalde, Gale, Holden, and Marth, represent the 4 candidate sites. And I want to tell you a little bit about why those represent terrific final candidate sites. If I could go to the next graphic, please. These show you little snippets for each of the 4 sites. Eberswalde in the top left, Gale crater to the right, Holden crater to the bottom left, and Marth Vallis to the lower right. Why do these represent great sites? Well, in Eberswalde crater, you land at what's perhaps the best delta on Mars. This is an incredible system of drainage into a crater that was probably filled by water, standing body of water that accumulated deposit, much like you would see at a river delta on the Earth. In Gale crater, as you've heard from Michael, there is this enormous stack, 5 kilometers thick, of layered material, which represents the opportunity to literally read chapters in a book of the history of past deposition on Mars. For Holden crater, you've got a system of dry rivers, much like you see flanking the edges of Death Valley in California, that drain down into a deposit of finely layered materials, which probably represent an ancient lake bed. So one of the most diverse river lake systems on Mars. And in Marth Vallis, you've got an incredibly detailed system of iron-rich and aluminum-rich clays that are layered and occur in a regional setting that represent a long history of ancient water interaction, and is probably the oldest of the 4 sites. So as John Grotzinger is fond of saying, these are sort of like different flavors of ice cream. All fantastic, but slightly different twists on that general take. Let me give you a couple of examples of the details of what we might have gone to look at with the next graphic. So for Eberswalde crater, as I mentioned, the best delta on Mars, well, you can see on the left here, and all the scale bars that you see here are in kilometers. The crater is represented, the colors represent low is blue and purple, high is yellow and red. The landing ellipse is shown there on the left, and the yellow box that you see represents a potential science target outside of the ellipse. The white box represents one within the ellipse. So all 4 sites represent a variety of high-value science targets within and around the ellipse. Outside of the ellipse in Eberswalde, you can see these scrolls that are produced as the drainage system came down and deposited the delta, much like we see on Earth, much like the places on Earth where we go to look for accumulated organic materials. Further out into the ellipse, we see older riverbeds and lake beds that would be explored on the way to the delta, providing us with a view of a setting on Earth that we're very familiar with. If we go to Gale crater with the next graphic, please. We see the landing ellipse is just to the north of this large mound of material. We would land on an alluvial fan, which represents material shed off the walls of the crater, this ancient crater recording ancient conditions, ancient processes on Mars. And then we would traverse to the south and access through a Grand Canyon-like gap into the wall of this mountain of material these finely layered sediments that allow us to go up and read the changing environmental conditions that have occurred through time. And then if we think about Holden crater, the next graphic, please. As I mentioned, this diverse river and lake system, we would land and access these dry alluvial systems, alluvial meaning much like the kinds of drainages that you see in Death Valley. Through craters, we can see the kinds of sediments that have been transported and reconstruct the environmental conditions, but ultimately access these finely layered materials that are further out on the floor of the crater and decide whether or not there was an ancient lake on the floor that could have accumulated the materials that might allow us to evaluate habitability. And then finally, with the last graphic, Marth Vallis. This is in the northern hemisphere. It lies between Marth Vallis to the east and Oyama crater to the west. Both within and outside the landing ellipse, there's this incredibly detailed stratigraphy of iron-rich and aluminum-rich clays that represents sort of a regional deposit. It's an incredibly ancient deposit and records something fundamental about the early interaction of water on Mars with those rocks and tells us something about ancient habitability. So I hope I've told you that all 4 of the final candidate sites represent an incredible opportunity for MSL. And as Michael and Michael pointed out, it was a very difficult decision to arrive at a final one. I will now let Don Sumner tell you a little bit about Gale crater and why it ended up being the eventual landing site.
So I had the joy of co-chairing the project's landing site working group, and we spent hundreds of hours discussing the sites, doing analysis of the sites, and trying to come up with the best science that we can do with the MSL payload. There are lots of flavors of ice cream, and we have certain ways to investigate those. And the project scientists and NASA felt like Gale was the best match for the goals of the mission, evaluating habitability, and also for the instrumentation that we have for MSL. So if we could get the first graphic. I'm just going to show a fly through into Gale crater and give you a sense of what an incredible place it is geologically. So we'll land in a landing ellipse, which is in the flat part towards us from the mound in the view that you see now. And within that, the landing ellipse, there's material shed off the crater wall that will give us a chance to look at what the Mars crust is like. That material was moved by water. Those rocks were transported by water, and that water either infiltrated into the ground or evaporated. And so there's also a unit that's very hard and dense that we're wondering about how it reflects that change of environment. So this is the youngest environment we'll look at with MSL. One of the fantastic things about this rover that Mike talked about is that we can go a long ways. And this allows us to rove towards places where the rocks are better exposed. Geologists like climbing up cliffs, and we get to go to those places with this rover for the first time on Mars. So the area of most scientific interest in Gale is at the base of the mountain, which we're zooming into here. And there we see mineral signatures of clays and also sulfate salts, and both of those are key classes of minerals that tell us about the environment on Mars and the interaction of water with that environment. And water is critical to habitability. So the rover will go towards the mountain. There are layers that we hope to see variations in this mineral that will tell us about how those minerals formed, how the environment changed through time. And based on the signatures from the orbital instruments, we expect to find variations in those minerals, and particularly in the sulfate salts, which will tell us about the water, how concentrated it was, whether it evaporated, the sources of the water. And that will give us a history of some of the ancient environments on Mars, how those changed, and help us evaluate the habitability of the planet. Those sulfate salts also contain water in them, and when they heat up, they release that water, and when they cool down, they can absorb the water. And so we have a great instrument package to look at how the water in those salts is exchanging with the modern Martian atmosphere, and it will give us a better sense of the water cycle on Mars, which has been very difficult to evaluate. Now, there is also, after the deposition of all these layers recording the environment, we had a time when you had water flowing down the mountain of Mars, and that cut a canyon a lot like the Grand Canyon. So that gives us the opportunity to read the environments through time and those changes, but that canyon cutting event also represents an environment that could have been habitable, where you have the flowing water, you have erosion, and you have deposition of those sediments at the mouth of the canyon, which is at the front view of the video here. And so the sort of suite of things that we can see at Gale represent a diverse number of environments over a long period of time, possibly tens to hundreds of millions of years, plus the modern environment. And so the Gale site represents just an incredibly rich suite of scientific investigations that we can do. And it's also just going to be an incredibly beautiful place. It will be a lot like a lot of the southwest areas like Monument Valley, where we have these steep-sided cliffs with the rover going in the shallower valleys between them. And we have the incredible instrumentation to characterize the texture and shapes of the cliffs and the mobility to travel through this area. So the science at Gale is going to be amazing, and it's going to be a beautiful site to visit. And John will tell us more about how we'll actually use the instrumentation to make some of these investigations.
Great. Thanks very much, Dawn. So what I'd like to talk to you now about is the way that Curiosity is going to explore the Gale landing site. But let me drop back to a minute to try to reinforce to you what an amazing precedent is being set right now with the MSL mission. As Mike talked about, one of the things that became obvious to the science team members in the community, and John said there was about 150 that attended these workshops. Our science team has 263 science team members at this time. And by the time that students are added to this, and postdocs and people like that, and participating scientists, we're likely to swell to 300 team members. What we saw happening was the unexpected possible outcome that we may be left with four landing sites, any of which might be chosen as the final landing site, that engineering would not kick one or more of them out. And that's what's always happened in previous missions. So we began to think about this in the project and how in the world we were eventually going to come together with headquarters and arrive at this decision. And as Michael said, it was not easy. Here's why. This metaphor of thinking about ice cream, it's a hot day. If any four of you go out afterwards and decide to go out and get ice cream, I'll bet you will not all get the same thing. And if somebody asks you why you choose between vanilla and chocolate, you're just going to say, well, it tastes good. It's what I prefer. And when you come down to four landing sites, that's basically what it comes down to. Which one feels right? And so in the end, there's no hard yes or no answer. You don't make a long list of things and put numbers by them and add them up and figure out what goes on. So we as a science team, as a community, we got together, and in the end, we picked the one that felt best. And so why does it feel good? Well, as Dawn was explaining, you've got a mountain of rocks that's 5 kilometers high. That's higher than the tallest mountain in the lower 48. It's taller than Mount Whitney. It looks like Hawaii. If you come sailing up to Hawaii, the thing about this mountain is that it's not a tall spire. It's a broad, low, mound-like shape. What that means, we can drive up it with a rover. So this might be the tallest mountain anywhere in the solar system that we could actually climb with a rover. So we think and plan around a 2-year mission, but we have a hope that if we lived longer, we might be able to keep going higher and higher up that mountain. That alone, it justifies sending the spacecraft there. Then when you start adding in the science goals that are on top of it, it turns out that the most attractive targets are at the base of the mountain, and we have a payload that we can address those with. So in the 2 years that we have to run this mission before the warranty expires, we can address the principal goals, which are the kinds of things that the Mars community would really like answers to. So what you can see in the first graphic that we have up there is the spacecraft with all the instruments that are on. And we have 9 principal investigators that have contributed instruments that are now part of the rover, which is down at Cape Canaveral. And those principal investigators are Dave Blake, Ken Edgett, Javier